Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks, Kent, and it's very nice to be here, and especially after so much travel today and all of the flight issues, and finally I get here. It's very nice. And especially, this trip is after an extra large Super Bowl game from Pittsburgh to Seattle. Okay, yeah, that's right. I know this is not a good time though. Okay, so anyway, today I would like to present some of my thesis research topic on combining diverse knowledge sources in information retrieval. And specifically, I would like to provide a set of conditional probabilistic models as tools to tackle this problem. And I will show you how can we apply these models on a set of large-scale retrieval problems. By the way, feel free to interrupt me if you have any questions. So I can just answer your questions and maybe skip some slides if necessary. So let me show you some example why we want to do the knowledge source combinations in information retrieval. So how many of you here have ever used a video retrieval engine recently? One? Only one? Okay. So the basic idea of video retrieval is very similar to text information retrieval. The only difference is that it will return the video clips instead of the text documents. So that's the only difference. So let's take this example. If we want to find the query, John Kerry is giving a speech. And this is a video clip that was relevant. Let me see if I can. Oh, there's no sound here. Okay. So you can imagine what he's talking about. This is sound. It's not important. You can imagine he's speaking something against the bush, and that's it, right? Okay, so if we want to find these video clips from a large database, how can we do that? Actually, there are several hints. We can do the text retrieval on the speech transcript that can automatically generate from a speech recognition engine. We can use the video OCR from the text overlay on the screen. From the audio side, we can do another things. We can try to do the speech music detections to detect whether this people is giving a speech or doing the music commercial, such kind of things. And from the visual side, we can do the face detection to detect whether this person, there's a huge face on the screen. And even fancier, we can do a crowd detection. Detect this kind of crowd on the backgrounds, kind of things. So all these informations are useful in their own aspects. And combining them turns out to be a very useful way to improve the video retrieval performance. Okay, let me show you another example why combination of knowledge sources is very important. This is related to meta search, of which the basic idea is trying to combine the output of multiple search engines. So let's take this query. George Bush is giving speech. And you submit these queries to 3 most popular search engines in the world. Well, and then you will be surprised how different the results you can get from all these search engines. For example, for Google, they will focus on the White House White House homepage. And from MSM here, you will focus on the news websites such as CNN.com. And from the Yahoo, they will return to a Wikipedia entries. So given there are so many differences between all these web pages, people naturally come up with an idea that why not just combine all these results together and give you a better rank list. So basically we can do that, merge them all together and give you a better rank list. So this is the basic idea of meta search. And actually this has been applied in a lot of commercial products such as the Revisomo.com or Katoo.com. And I'm expecting that there will be more and more applications like this in the future. Besides the multimedia retrieval, meta search, actually there are many other applications that can benefit from combining diverse knowledge sources. For example, in the web retrieval, you can combine the content informations like the document text or the anchor text with the hyperlink information such as Hub Authority score or the PageRank score. From the cross-lingual IR, if you have a parallel document text, then you can do the retrieval on English side or on the Chinese side or on the other language, and then you can merge all these results together. Also in a retrieval-related task called the multi-engine machine translations, you can run several different kinds of machine translation methods, maybe like the example-based machine translation, statistical-based machine translations, and then you can combine all the translation results. So all this, there are so many other possibilities that I cannot list here, but all this result shows that it's very important for us to develop effective combination models that can help to improve the performance in information retrieval tasks. But combination is not easy, especially when we are, in most of the case, we are combining a large number of diverse knowledge sources. For example, in the multimedia retrieval, in the video retrieval, we can generate more than 100 knowledge sources together. And in the web retrieval, it's possible to generate more than 10 types of knowledge sources. And even worse, all these knowledge sources usually generate some outputs that are not compatible with each other. So we have to do some normalizations to make them into the same space. And the worst case, well, the worst thing is that the optimal combination strategy is different from queries to queries. So it's not always it's not the best idea to use the same combination strategy for every possible queries in the same time. So our research topic here is trying to develop some principal methods to handle all these problems. By principle here, we mean our measures should be learned from a large scale of training data and should be scalable to a large number of testing data. So before I go into the details of how our algorithm work, let me first go through some previous work on this field. So among a lot of combination methods, the simplest approach is trying to do the so-called query-independent combination. This is quite simple. Actually, it means that we should always use the same combination strategy for every possible queries. Roughly speaking, you can classify this type of approach into two types. One is called the predefined combination approach, such as you can take the maximum, take the minimum of all the retrieval outputs. Or if your retrieval engine can output some probabilistic outputs, you can do the multiplication, or you can do the border fusions on the ranking space. Another type of approach is called the learning-based combinations. Actually, so the basic idea is trying to learn the combination strategy from a large amount of training data. So in the literature, there is a huge amount of such kind of work. So you can do the weighted linear combinations, or learn the support vector machines, or logistic regression, such kind of things. So this method, all these methods are very simple to implement, and they are very efficient. But since they did not consider any query informations into combination functions, their performance are usually limited in practice. So people will begin to think, since we don't have any query informations in the combination functions, why don't we just consider query informations into the combination functions? Can we do this? So recently, some researchers began to propose the so-called query class-based combination methods. The basic idea is trying to put all the query information into a limited number of query classes. It typically includes two steps. One is do the query class classification. You first associate the query description with one of the predefined query classes, such as finding people query, finding object queries, or finding different kinds of things, query, and so on. And then based on the query class predictions, you can choose the best combination strategy for this specific query class. So these methods can somehow incorporate the query information into the combination functions, although it's only in a limited number of query classes. And as you can see, this method has attracted more and more attention in the IR community recently. 2 years ago, we introduced this approach to the video retrieval community, and now it's accepted to be the best combination approach overall for the video retrieval. And query class-based combination is also useful for the web retrieval. So in the track, web retrieval track, they basically will classify the query into 3 classes. One is the name page finding, forgot something, topic distillations, and another class, I forgot that. Anyway, sorry. So there's another emerged directions which is called the query difficulty predictions, by which we means you can predict whether this query is difficult to predict or not. So if this is a simple query, you can use some simple combination function. If this is a difficult query, maybe you can do some tricky things on the combinations. And query class-based processing is also useful for the other type of stuff, such as the topic detection and checking and question answering. So the success of all this approach shows that it's very useful if we can incorporate the query information into combination functions. However, the query class-based method is not perfect. There are still several limitations in this kind of methods. For example, they do not provide any probabilistic semantics for the relevance and query classes. So it prevents us from using some standard machine learning technique or maybe statistical learning technique to learn all this strategy from the training data. More importantly, all this query class has required some human experience to define, and typically it's not practical, especially when we have a large amount of training data. And so this is pretty labor extensive if we want to define, let's say, 100 query class. It's very difficult to define by a human. And it's very difficult to model the mixture of query classes in one query. And furthermore, we are not able to determine what should be the optimal number of query classes given the training data. So it would be a better choice if we can learn some latent query classes automatic from the training data without any human experience. So that will be our perfect choice. And finally, the process of query class classification and combination way optimization are typically separate with each other. So you are not doing the joint optimizations on both levels of processing. This is usually not optimal. Yeah, that's right.
More data than what you would if you were to automatically detect the list or have latent class?
No, we are not claiming this. I think what we are claiming is that we should automatically learn the query class from the training data instead of ask a human to define the query class themselves. Especially when you require, maybe you want 100 query classes, it's very difficult for a human to define such kind of things. Yes. So usually current application will only use 3 or 4 query classes, but you cannot do more. That's a problem. Yes? The training data will be like the binary relevance judgment from the people for each query and each document. So you can... sorry?
So then it's already supervised.
Yeah, that's right, supervised method. Actually, that's right. Okay, so no other questions? So given there are so many problems here, can we do it better? Yeah, of course the answer is yes, right? So, and we would develop a set of conditional probabilistic models to automatically learn the latent query classes from the training data, and we showed you how we can adapt this combination function on a per query basis. And here's the outline of my talk. I just introduced why we should do this, and next I'm going to present two different conditional probabilistic models to combine the knowledge sources. One is called a probabilistic latent query analysis, and the other is called a probabilistic local context analysis. And I will apply these two useful techniques to a large-scale retrieval task, which is video retrieval and meta search. And finally, I will conclude my talk and present some future directions to you. So let's start from the most general case. Typically, a probabilistic retrieval model will treat the IR problem into an uncertainty inference problem. So basically, it's going to estimate the conditional probability of Y. This is a document relevance given the document and query queue. Once we have the conditional probability, we can use the probabilistic ranking principle to rank the document and give the user a ranked list based on the descending order of the conditional probability. So now the problem boils down to how can we estimate the conditional probability here. So as our starting point, we will model these things using a logistic regression model. So here, let's say, so it's basically modeled as a logistic function of the sum of a set of a weighted sum of a set of ranking features here. Why do we want to choose this model instead of the generative model that was common in the text retrieval world? Because it has several advantages. For example, it has less model assumptions than the generative model because it does not consider any dependency between, assume any independence between the features. And from the experimental results, it has shown that the conditional model will provide better performance if we can provide the model a sufficient number of training data. So that's why we want to choose this model as our starting point. And actually, this model is very useful for a large number, a number of text processing tasks, such as text classification and information extraction. So in this model, there are two components. One is a set of ranking features that can be generated from multiple knowledge sources. And the other is the corresponding weighting associated with each ranking features. So let me use the next few slides to explain how can we extract the ranking features and how can we estimate the corresponding parameters for these features. So let's take a close look at what is the ranking feature here. So roughly speaking, the ranking feature can be generated from multiple types of knowledge sources. Let's take this example of video retrieval. We can have two types of ranking features. One type of ranking feature is the output from some unimodal retrieval experts, such as the text retrieval on speech transcript or image retrieval based on the image example provided by the users, such kind of things. And another type of ranking feature is the detection results of different kinds of semantic concepts. So the semantic concepts here can be very general, such as the face, anchors, or commercial shots. So the face detection results can be very useful for video retrieval when you are finding a person, or the commercial detection results can be very useful if you want to find some news-related results. So these are two types of ranking features that can be defined by video retrieval. Similarly, for meta search, we can also consider the output from multiple search engines as one kind of ranking features, and we can use some weighted sums to combine the outputs of search engine into a final rank list. Hopefully, it's better rank list. Actually, there are a huge amount of related work on this aspect, but I'm not going into the details of how can we generate all these ranking features. And given you have all these ranking features, the next problem is is that you have to estimate the corresponding weight for each ranking features. Since we cannot collect the ground truth data for every possible queries that user is going to submit, here we will face another problem, which is that how can we estimate the combination parameters for some unseen testing queries, given that we only have a collection of training queries and their relevance judgment? How can we do that? As I mentioned before, there are some previous methods to do that. For example, you can do the query independent combinations. So you will always use the same combination strategy for every possible queries. But this is not flexible, so it does not take any query information into account. So this is not good. And the more advanced model of query class combinations, which is current state of the art method, can improve the performance, but it will need some human experience. So now we will try to find some way to do better on these two methods. And our solution is called the probabilistic latent query analysis. So this method is built on three underlying assumptions. So first, I'm assuming that each query can be described by a mixture of latent query classes. And so these latent query classes are capturing all the information from the query space. And then I'm assuming each query class will associate with a set of combination weight, where the combination weight can be learned from the training collections. And finally, when you have a new query, you can automatically predict which query class the new query belongs to, and automatically determine what's the best combination weight you should use for this specific queries. So now you will see all the query information are encoded in this kind of latent query class, and you can automatically learn the query class from the training data. But now we still have three problems here. One is that how can you associate the query with three query classes? How can you learn the combination weight for each query classes? And finally, when you have a new query, how can you estimate which query class are associated with them and predict what's the new combination weight? So in the next few slides, I will show you how can we handle this problem one by one. Okay, so let's start with the basic version of the probabilistic latent query analysis. And the basic idea is that we introduce a new latent class variable into the logistic regression function, which is here. So in this formula, we are doing two-step processing. The first is that we first sample the query class variable from a multinomial distribution depending on the queries. And then we will use the corresponding weighting to combine the knowledge sources. So based on these graphical models, you can see the latent query class variables are serving as a bridge between the queries and the document's relevance variable. And it naturally combines the query class classification process and the combination weight optimization process into a unified framework. So maybe someone has found that it has some similarities with Thomas Hoffman's probabilistic latent semantic indexing model, but they are doing that on the Word document space. Similar, but we are doing that in the query and combination weight space. So that's two different things. And from another viewpoint, if we are considering the query class-based combination as a hard query clustering approach, these methods can be considered as a soft query clustering approach because it provides some probabilistic assignments to each queries. Okay, so there are several advantages of this approach compared with the query class-based combinations. The most important thing is that now we don't have any manual definitions on the query class, so you can automatically learn that from the training data. And we allow to handle mixture of query class in the single queries. So for example, you have a query finding Bill Clinton's in front of the US flag. You can consider this query as a finding person query and also a finding object queries. So 50% finding person and 50% finding objects, that kind of things. And finally, using some statistical model selection criteria, you can automatically determine what should be the optimal number of the latent query classes, given the training data we have. So for example, you can use the AIC and BIC, such kind of things here. So now it looks like everything is solved. So you can just carry a bag of training queries and their relevance judgment, throw into the pLQA models, do optimization, and you get the retrieval results you want. So is that the case? No. This is the problem. There's a huge problem in the basic version of the probabilistic latent query class query analysis model, which is that the mixing portion here is specific to each training queries. So it's not a well-defined probabilistic retrieval models. And, I should go back. And if we want to extend all these parameters into some unseen queries, it's impossible in these models. So we want to find some way to handle these problems, which is trying to extend the pLQA models into some unseen queries that was outside the training data. So here's how we do this. The new approach is called the adaptive probabilistic latent query analysis. By this approach, we means we will first represent the queries as a set of query features. So the query features can be defined very flexibly. For example, it can be defined whether this text query contains a specific person name, whether this text query contains a specific object name, or how many objects does this query mention, let's say 3 or 5. So after you represent the query into a vector of query features, and then you can define the mixing portion as a softmax function over the query features instead of over each training queries. So now the parameter was associated with the query features instead of each training data. And in this way, this allows us to handle the training data very flexibly. So we can handle the unseen data without retraining the whole models again and again, and this will become very practical in the retrieval applications. So in this graph, I'm trying to visualize what's the difference between the methods we discussed before. So the rectangle here means a space of 2 different combination parameters. And the triangle here means a simplex of 3 query classes. And if we are doing the query independent combination, it means we only choose a fixed point in the combination parameter space. And if we are doing the query class combination, we are basically choosing the corner on this query class simplex. So it's not very flexible, but it's a little bit more flexible than the query independent combinations. So if we are doing the basic version of the probabilistic query analysis, we can assign some mixture of the query classes in the specific training queries, but we cannot extend the mixture of classes to other unseen queries. So we propose this adaptive probabilistic query analysis, which can provide a smooth distribution over the query class simplex, and it naturally can be extended to the unseen queries. So these 4 methods involve in a way that the query class distribution become more and more flexible and will be capturing more and more query informations. Yes?
What happens if you just add those query features to the basic version rather than doing
That would be different.
It'll be different, but
Yeah, that's right.
in practice, it's a little
So by adding the query features into the logistic regression, so do you mean a early fusion technique? So it's like you. Okay. Yeah, exactly. So as to my. Okay.
I hate to be awful, but can you repeat the question?
Oh, I see. Oh, yeah. So the question is that if I'm adding the query features into the logistic regression models directly, what should be the effect comparing you are doing the proposed method here? So is that the questions? So I think in this model, if you are directly adding the query features into the original model, since we have a larger amount of knowledge source to combine, let's say in video retrieval, I have 100 features in the original logistic regression models, but typically the query feature you only have 10 or 9 such kind of features. So basically the number of the query feature is much less than the knowledge sources you want to combine, and their effect will be overwhelmed by the other features. So you will almost just see no effect from the query features if we do that that way. So in another view, you can view this as a early fusion problem versus a late fusion problems. So you are either doing the fusions on the joint space of the knowledge sources and the query features, or you should first do the fusions on the knowledge sources and do the fusions on query features and finally combine them together. So I'm not sure if that answers your questions. I mean, there are basically two types of things. So there are some argument here. For example, in the video retrieval, you can have color features, you can have texture features. So someone arguing that you should combine the color feature and texture feature together into a huge space and do classification. And someone is arguing that you should do color classification first and do texture classification first and then merge them together. Yeah, that's right. Yeah, that's right. Mm-hmm. Well, theoretically it's possible, but in practice I don't think that's the case. I mean, yeah, I have to try that. It doesn't work. I think the problem is because the query feature was overwhelmed by the knowledge sources outputs. And that's why you want to separate these two things together. But I think that's a good question. So maybe we can sort of compare the two problems I mean, in the fair settings and see what exactly is the performance. So sorry, I have to repeat the problem. I forgot to repeat the problem. Okay.
I don't want to get you off.
Okay, sure, definitely. So any other questions for the things? Okay. Okay, well, huge lot of math here, but you don't really need to understanding all this stuff to understand the whole talk. Basically, you can use the Bayesian information criteria to determine what's the optimal number of query classes. So it's very simple. It has a solid statistical foundation. And if you want to do the maximum likelihood estimation, you can use the EM algorithm. So you can iterate the E step and N step until they converge to a fixed point. I guess most of you know what's happening here, so I'm not going to the detail. But if oh, that's a good point. So so the question is that how do you initialize the starting point for EM algorithm? So basically what we are doing is that you randomly take a query. So if you want to learn, let's say, 6 latent query class, so you take 6 queries from the training data, and then you assign the combination weights by optimizing each specific queries one by one. And then you do a joint optimizations over the entire query space. So that's how I optimize it. Okay? So, well, you don't need to understand it at all. Yes?
So, okay, so ideally your your query classes will be chosen so that they have the most variation in the combination.
Yeah, ideally, that's right. That's right.
So does this likely go towards that ideal point, or does that depend a lot on the initialization?
It's somewhat dependent. So the question is that ideally I should choose the query class distribution as diverse as possible. So does this estimation goes towards this ideal case, or will go towards another case? Yeah, I think it's somewhat depending on the initial conditions, but it's not very significant as depending on the initial conditions as you think. I'm not sure how many you are thinking. So basically what we are doing is that we choose the first query and we choose another query that was most diverse with this query, and we choose the third query that are diverse with these two queries. So it's kind of an iterative selection of the queries, and we use all these queries to do the initialization for these models. So it can somehow take care of the diversity issues, but I'm not sure that's the best solution for this problem. But at least we try something in this direction.
What do you mean by diverse query?
Oh, sorry?
Well, how do I say this query is farthest from that query?
Ah, yeah, that's a good point.
Do it in this latent semantic distance space?
No, I'm doing that in a very naive way. So maybe like I'm using that two query to train a set of conditional combination weights, and I calculate what's the likelihood if I'm likelihood difference. I mean,
Like a KL distance?
yeah, it's actually what's the maximum reduction of the likelihood. So I choose that kind of thing. It's kind of like a heuristic stuff. There's no some fancy statistic there. Yeah. So this is the open directions to choose the initial points for this model. So I would like anyone here would like to try to explore these directions. I'm just doing some simple things here. Okay. If you are not doing the query selection, the local optimum. So the problem is that how serious the problem is for the local optimum. I think if you do not do any initialization methods, the local optimum problem is very severe. But if you do some simple things like what I have said, so the local optimum is not a big issue here. But you have at least to do something like that. I mean, maybe some stupid things, but it has to be something. Yeah. Okay, so let me move on. So next will be the experimental results for this model. And I will try to apply this technique to two different applications. The first application is the video retrieval, and I'm using the video check as our data set to evaluate. So how many of you have ever heard about the check vid competition? No one? Really? How many of you have ever heard about the check? Okay, that's great. So check vid is a sub-check of check. And that was a competition specifically for video retrieval. But we have our own 2 days workshops that were separate from the check conference. So most of us did not get many contacts with the other check guy. But as you can see, the partition rate is growing higher and higher in these 5 years. So we have 62 last year, and this year we will have more than 80 participants around the world. And the competition is becoming tougher and tougher. So last year we are dealing with 200 hours, more than 200 hours video. Of course, it's much smaller than the MSM here, but it's already a very large amount of video data for academia research. So we use that kind of things, and NIST will officially provide 25 multimodal queries every year, and we use 50% as training and another 50% as testing. So here's the story. Since this thing is so tough, and it's happening in the summer, everyone is laid back at that time, want to travel. So my advisor just try to offer some free pizza every week, but you have to get good results. If you get good results, you can get a gourmet pizza, but if you get bad results, you have to buy the pizza for everyone. So, well, since you know, everyone here will know free pizza is always the best motivation for a graduate student. So these things really work, and last year we get the #1 in the automatic video retrieval competition. So very good. So always use a free pizza. I think this is a good way. Sure. Yes. Yeah, it's not a lot actually. Yeah, I mean, compared with what the query has in the MSN here, it's very tiny. But NIST only provide 25 queries because of the relevance judgment issues. They don't have too many people to judge the ground truth for all these 25 queries. Basically, they only have 3 or 4 people, and they have to, for each query, they have to find the ground truth in this 200 hours video. It's very difficult for 3 or 4 people to do that, so they only provide 25. The ranking feature is the FI there. So that's the basic. Oh, I have to explain that. So 6 retrieval expert means the text retrieval based on the speech recognition, based on the speech transcript, and based on the VOCR, or an image retrieval on the color histogram, on the edge histogram, such kind of things like that, because they also provide some image examples as our queries. And that's why I say this is a multimodal queries. They provide a video example and also image examples to us. And for 74 semantic concepts, we have face detection, anchor detection. We even have some outdoor detection, a lot of things. So we have 75 terminology there, and we train the classifier on top of it. Yes? Yes?
So your queries don't include any text?
No, they have. So the question is that the query did not include any text, but they have. They have the text description. They also have some video example and image examples.
And does the data come to you with any text annotation? Closed caption things?
Yes. They have the closed caption and they have the speech recognition. So, but unfortunately, last year they don't have any closed captions. So our group is running the speech recognitions on the data and provide to all the other participants. Yeah. Yes. A lot, actually a lot, especially for let's say for the sports type video, such as finding basketball or finding soccer. You see there's a lot of similar backgrounds for the soccer games and for the basketball games. So image retrieval will be very useful for such kind of things. And if you are finding persons, the face detection will be very useful. And the face detection currently is very accurate. Maybe it's more accurate than most of you think now. It will be around 80% or 90%. So there will be. Sorry, I did not hear.
You were saying,
was
there a specific query that asked you to look for soccer or basketball?
Yeah, they have that.
Can you describe what the query was?
So let's say for the soccer query, so they will have a text description saying that find me a video clips of soccer game, and they will have an image example showing what the soccer game looks like. And they will also have a small video clips shows what the soccer game is going on, and that the people are shouting and they see a goal, a lot of stuff there. So that's kind of query we get from the NIST. Hmm? So you mean using all this image retrieval stuff and video retrieval stuff? So that's a good question. Actually, we think about that a lot. What the NIST people want, because they are sort of related to the military part, and they have a lot of video analysis. They want to find some military-related things, and they will have a lot of images that was related to the military. So they want to find that in a huge database. And that's why they fund our research to doing that. That's why they set up this track with Retrieval to do that. They exactly want us to use the image example and video example to do that. But maybe for general users, let's say in MSN search and Google, submitting an image example might not be a good idea. Maybe you can do a relevance feedback, that kind of stuff. But directly submitting an image example might not be a good idea. But the semantic concept is useful. For example, you can do face detection, you can do outdoor detection, such kind of things, and then you can index offline. And you do a retrieval, you can just take the information out and combine them all together. So that kind of information could be very useful. Yeah.
The text features have some speech recognizer. Did you take into account the errors of the recognizer?
They have a lot of errors.
Then you just put whatever come up, or do you provide a test so that
currently, yeah, actually we provide a rank list from the text retrieval. So we saw them from the top one to the last one. So it's not an M best, it's a, let's say 100 best or 100 best. So, yes. Yep.
The features or video features are fairly high level face detection.
Yeah, that's right.
And background.
Yeah, that's right.
So I would assume that you directly apply the same system to word verification wouldn't work at all.
You mean for such
For finding tags.
finding tags? Yeah, finding tags is the one that doesn't work very well. I mean, for this kind of query. So that's why if you want to find tags, actually there are several hints you can help. You can see maybe tags is always on. It's in the outdoor, and you can use the outdoor detections. You can use the vehicle detection. Let's say there's a vehicle on this screen, so you can combine these information together. Of course, I agree. Finding tags.
So the idea is to always specialize features of the application and then apply this into the top. Maybe try to work with low-level features.
I think you have to also work on the low-level features. I mean, a lot of people are working on the low-level feature, and a lot of people are working on the high-level features. I mean, a lot of people are working on the combination, and I'm the guy working on the combination stuff. I'm waiting.
I'm worried we're derailing your talk. You should take control.
Okay, sure, definitely. So maybe we can talk offline. Yeah. So I think if this is interesting, I guess I need to skip some slides since it's already 4:20. And so here are some results. As I mentioned before, you can use the probabilistic latent query analysis to automatically learn the query classes. And now I want to show you some example of what's the latent query class you can learn from the data. In more details, I classify all the Treco 5, which is last year, queries into 5 groups. And on the right-hand side is the results you can get. So as you can see on the first group of data, it's basically all the specific person finding types of query. And on the second group, it will be something related to the sports because they always use image retrieval or video retrieval, such kind of technique. And all the other things, all 3 groups, are somehow related to the object finding. But if you take a closer look, you will find that for the first one, it's some static objects. So you can use the motion detections to delete some irrelevant video clips out. And for the group 4, it's basically finding some object that was in the outdoors instead of the indoors. So, well, since this clustering results is pretty intuitive to interpret by user, I think the probabilistic latent query analysis is doing a good job here. So next, let me show you how can we detect the optimal number of query classes. So basically what you are doing is that you can first calculate what's the log likelihood curve. And then you add the Bayesian information criteria on top of it and find the minimum points on this curve. Oops. Sorry. That's high-tech stuff. Okay, so you can find the minimum point here. So from our training set, we can say the number of 6 query classes will be the optimal settings given the training data we have. And we showed you some examples how these things work in the testing set. So it looks like from the beginning, if you are adding more and more latent query classes, the retrieval performance will growing higher and higher. And just after that, you will get a lower performance because of the overfitting effect. So as you can see, the 6 query classes setting might not be the best one for all 3 settings, but it's already close to the best performance what we can have. So I think our predictions for 6 query classes are pretty accurate in the testing sets. Okay, finally, I want to show you some average performance over all 3 abstract tasks. So if you're simply doing the text retrieval, let's say this is a baseline. If you do the query independent combination, you will get 40% improvement. And if you do the query class-based combination, well, you can get more improvement, let's say 38% here. And if you use the proposed methods to do that, we can get an additionally 52% improvement. Yes?
Aren't the error bars each year you only have like 10 or so areas in your test set?
25. Yeah, that's right. So
basically you have 25 queries total, half is training, half is test.
yeah, that's right.
Is this significant? I think the error bar is giant.
Oh, so we do the significant test here. So basically, you can see this is a 10% mean average precision, and this is 15% mean average precision. And by conducting the significant test, you will see these 2 things are statistically significant. These 2 are not, but there are some improvement there. And we also want to emphasize the fact that all the improvement bring by the proposed method is completely from the training data without any human knowledge. So you can do that by throwing into some training data without just hurting your brain muscles stuff to come up with some query class. So I think that's very good properties, especially if you have a large amount of training data. Yes? Okay. Yeah.
What's the granularity of your and the results that you're expecting? Are you going second to second on the video? Do you have to match?
We are doing the video shot retrieval.
So you segmented it already?
Yeah, that's right. Typically, a shot will be spent 2 or 3 seconds. So you will want to find 2 or 3 seconds of video clips in the database. Yeah. So yes.
Can you try to just do the database of queries to see how they're split? Because that would be much easier. You don't need judgments on relevance of the documents. Just make sure that what you're getting there. For me, the first 2 classes made sense. The rest of the classes didn't make any sense.
Okay. Yeah, that's right. That's.
And I don't know. I could have found different criteria to make sense of 3 queries together.
Yeah, that's right. I mean, for that one, for the illustration slides, I'm just trying to illustrate what's the query class that can be learned from the training data. Of course, this kind of something like unsupervised learning technique. Of course, it's a supervised, but if you want to automatically learn the latent query class from the data, it's very, for most of them, it's very difficult to specify what exactly is the meaning of the query classes.
But it wouldn't be that difficult to generate one query, right? And just to see if it makes sense what you're getting.
Sure, definitely. I think, yeah, but we did not do that now. I think that's a good future experiment for my thesis because I haven't finished that yet. Yes? Sure.
So on the previous slides,
Mm-hmm.
what are the error bars?
This one?
It seems like both are black. I'm just wondering what the
Oh, yeah, there's a problem here because, well, for the Trickle 3, the performance is much higher than the Trickle 4 and Trickle 5. So it makes the difference between Trickle 5 and Trickle 4 seems to be minimum. But in fact, if you just plot them into a single graph, you will see a lot of huge difference there. No, I did not plot the error bars there. Yeah, it's a good suggestion if I plot the error bars. I guess I have more work to do in the future. Yes. Okay, I guess I have to skip some slides. Okay, so you can achieve higher performance without manually defining the query classes. Another application is related to meta search. And we will use the track K collection to do that, I assume. So we will combine the top 10 search system to achieve that was achieving the highest average position. So here's the results. As you can see, we also plot the Oracle performance here to show that what's the possible performance achievement if you are doing the linear combinations. So that's the bad things you can do, given that you know all the ground truths in the testing sets. So as you can see, doing our proposed approach, we can do better if we do the query independent combinations. And of course, the potential of improvement here is much less than video retrieval. So I think 4% is a reasonable improvement if we are using this kind of stuff. But it still shows that the proposed methods can benefit from flexible combination weights. Okay, a short recap. So we basically introduced what's the basic version of the pLQA by introducing a latent class variables into the logistic regression function. And since this model cannot handle the unseen testing queries, so we further developed the adaptive pLQA, which can handle the unseen queries by defining some explicit query features. Of course, the adaptive pLQA is not perfect. So we further extend this technique in, so one is called the kernel pLQA by using their, a Mercer kernel to describe the query space. So now you can describe the added distance between queries or some pairwise distance between the queries instead of using some explicit query features. And we also developed another technique called hierarchical pLQA, which the idea is similar to the latent terrestrial allocations. So we are trying to model the variation of the combination parameters inside a query class. So it doesn't like now each query class was simply associated with a single combination weight. So now in the hierarchical model, we assume each class was associated with a distribution of the combination weight distribution. Well, I have said a lot of good things for the pLQA, but there are some bad things here. So the biggest disadvantage for the pLQA model is that the power of its power is limited by the training data. So if you don't have enough training data, then this model will not work very well. And given a limited number of training data, the weight of many ranking features are simply set to 0 in our models. But these so-called unlearned features are sometimes useful for some specific queries. So let's say if you are dealing the query of finding some ships. Of course, you can learn some ways from the training set, but you will find that the ranking feature of ocean and ranking feature of outdoors will be very useful for this type of technique, for this type of queries. But since the ocean is rarely appear in the training data, it's very difficult to learn a combination weight for these specific ranking features. And even worse, what if we don't have any training data at all? How can we apply the probabilistic latent query analysis here? So can we improve this and do a better job here? The answer is yes here, of course. And that's why we propose a new combination models called the probabilistic local context analysis. So the basic idea is quite simple. I think so. We're just assuming the combination parameter of those unlearned ranking features to be a latent variables in the combination functions. So in more detail, we are basically assuming that from the query, we can generate a set of initial search results first. These search results can be generated by any kinds of methods you can come up with, such as text retrieval, or you can do the fancier probabilistic latent query analysis. And then we will assume the combination parameters for the other features are latent variables. And they will pose a joint effect on the document's variance variables. So the hope is that the information from the initial search results can flow through this node to affect the nodes of the unlearned variables. So provide some information here so that we can automatically discover what should be the useful ranking feature and what should not be. So based on this idea, we naturally formulate the whole problem into an undirected graphical model. So as you can see, so the undirected graphical model formulation is important here because the information from the A here can flow through some unknown variables to the combination weight of nu. If you use a directed graphical model formulations, there's no such kind of effect. And based on this undirected graphical model, we can naturally come up with formulations like this. We don't need to fully understand that. So in brief, so we are introducing an interaction terms between the relevance and the combination weight. We are also introducing prior terms that was related to the unlearned variables that you can automatically predict from the queries. So since the inference for this problem is intractable, so we will use some variational inference to do this. The basic idea is that you can iteratively maximize the variational lower bound of the log likelihood function until it converges to a fixed point. But don't be scared by the variational inference here. It's just some fancy name. Actually, this thing runs pretty fast. It will typically converge in 10 iterations. So I think it's still practical in practice. So any problem for these models?
So
Yes?
you're trying to learn
Hmm?
search engine.
Hmm?
Somebody made a search engine.
Hmm?
The results are very, now you're trying to learn
What's the... Yeah, that's right. So the question is that I'm trying to learn the search engines. So I think a more correct way to say this is trying to learn the weight of the search engine. So is that how much weight I should give to this search engine instead of the other search engine.
documents that you get back in the search engine, you learn feature.
Oh, no. I'm only learning the weight. It's possible to learn feature here, but because I'm not doing that. But it's possible. Yeah. So, this is the probability. Yeah, this is a new model I propose. And some results here. So here I showed you how the pLCA is useful in finding some useful ranking feature automatically from the query descriptions. As you can see, we use the pLQA as our initial search results. And in this learning process, over 50 ranking features are ignored. So in the pLCA, we can see how we can use these 50 ranking features to improve the retrieval performance. So for example, in the query of Tony Blair, we can automatically detect the government leader. This ranking features, it's useful for detecting the Tony Blair. And for the helicopters, we can automatically detect the airplanes and skies are useful for this type of queries. And we also detect some negatively related queries. For example, for basketball, we can detect that commercial is not related because there's no commercial at all for a basketball. For a basketball shot. So this shows the usefulness of the new models. So, okay.
Things like the even across the
You mean, actually the leader here is not a word, it's a classifier. So it means we have a government leader classifier, and we can learn this classifier from the training set. So in the testing set, we already have a result say, this shot is 0.9% as government leader, and the other shot will have 0.1% probability to be government leader. So that kind of thing. So it's not a simple word. So that's why I called it ranking features or semantic concepts instead of words. So.
How does features, can you hear that first thing?
Oh, yeah, that's right. So I have mentioned that we have training set, right? We have training set and we have testing set. We are using the training set to train the classifier because we have the ground truth for the government leader in the training set. So we can generate the classifier and then apply to the testing set.
So the leader, the concept of leader in the training set already exists.
That's right.
The human already label that?
Yeah, you can label that or you can automatically generate that. Yeah, in this talk,
Did you automatically generate it or you?
we automatically generate that. Yeah. So in last year, this is actually a task in CheckVid.
That means when you generate concept leader, did you automatically label that? You come out with the class.
Yeah, that's right.
Your system automatically tag that as a leader?
Yeah, that's right. You learn that from the training set.
No, but the training set, I mean, when you have the training set, the leader concept already tagged to the training set.
Oh, yeah, that's right. That's right.
From human, right?
That's from human, exactly. So there's a huge project called LXCon recently. So their goal is to annotate 1,000 semantic concepts on 200-hour videos. So you can do the classification on 1,000 concepts. Of course, this will take a lot of time. Yeah, but we can use that kinds of data to do the semantic concept detection. Their hope is that we only need to define a small set of semantic concepts based on the zip law, and then we can just throw the other things away, and that's their hope.
I want to make sure that you get your points out, so if we're being too disruptive, just put us.
Okay, sure, definitely. Thanks. It's going to finish, actually. Okay. So by applying the pLCA approach, we can see there's approximately 10% improvement over the baseline model. And I think this is pretty reasonable, especially this almost comes for free. You don't need to do any more annotations. You don't need to do any more training. You're just automatically predicting from the queries. So I think this is pretty reasonable.
8% improvement out of 25 queries, how much it means?
Oh, no, let's say we don't have 25 here. Actually, each year we have 25, so it's 75. Yeah.
But
So,
how does that be used for training?
no, basically we are actually doing the training on the other half of data instead of the queries. So in the data, for the training set, we design some queries ourselves. So we are not using this kind of queries. So we design the new queries and we use a separate set of training data. And for the testing set, we use a different set of data and also a different set of queries. So these two things are separate. So I'm not sure if that answers the questions. Yes. Okay. So maybe we can talk offline. Okay. Okay, meta search. Meta search, the improvement over meta search is always lower than video retrieval, but it seems the potential of the improvement is very limited. You will see the oracle here is 65%, and there's not much room here. But after applying the pLCA, we can still see some improvement, and I think this is good. Okay, so here's the conclusion of the talk. And in this talk, I have developed a series of conditional model as the basic framework to combine multiple knowledge sources. And I provide two types of conditional model. One is called a probabilistic latent query analysis, and the other is called the probabilistic local context analysis. So for the first type of model, we can automatically discover the latent class from the training data without any human without any human definitions. And it can automatically decide what's the optimal number of query class based on some statistic model selection criteria. And for the other type of model, we can automatically discover what's the useful knowledge sources in some specific queries without doing any training at all. So finally, we have applied the proposed approach into two large-scale retrieval tasks. One is video retrieval, and the other is the meta search. Okay, some other future directions. So you can do some theoretical refinements on top of these models, or you can do a larger scale evaluation. I think this is extremely important if we want to apply this model in practice. I think MSN here will be a very good, will have a good test bed to test whether these models will work or not in a larger type of database. And there are many other potential applications for this type of model, as long as you are trying to combine different knowledge sources. For example, we can do the web retrieval, which I haven't done any experiment here. You can do that on cross-lingual IR. You can do that on machine translations, or even you can do that on people tracking stuff. So you can combine different tracking algorithms based on the environment change. So there are so many possibilities that can make use of this kind of model. And I think it's very interesting to see whether I can do that later. So the final slides, I want to give some introduction to my other PhD projects. And if you are interested in these projects, we can definitely talk offline. I have also involved in a project called KMedia. The basic idea is trying to do the video surveillance in the nursing room environments, so you can calculate the statistic of each patient and provide the reports to the doctors automatically, let's say each month. So if the doctor finds there is some novelty in these statistics, they will go to visit the patient and see, well, what's wrong with you and can we do something better, so such as it talk less than before, it walk less than before, something like that. We have several papers on the human tracking, activity recognition, active learning, and learning with some side informations. I also do a lot of things on the machine learning with application to multimedia data processing. So I have do some research on the concept relational modeling. I do something on the rare data prediction. How can we improve if we only have a few positive data? And how can we do the joint modeling on the text and images? And how can we learning with the ranking information instead of only using the binary positive and negative information? And I also do some learning on, do some machine learning stuff on multiple views, such as the co-training and improvement on the co-training. I also do something on the genre classification and text classification. I apply the maximum entropy models and also the kernel fusion technology with Yan here to handle the text classification stuff. Speech recognition to some graphing to phoneme conversion. Recently, I'm involving into a medical video research, which is trying to determine whether this video has a tumor or non-tumor. So as said by my advisor, this is a Nobel Prize type of research. If you can do this, then you can definitely win a Nobel Prize on top of it. But I'm not sure whether we can finish there or not. Finally, I have developed an open source MATLAB package for all-purpose classification algorithm. I think it's already shared on the web now, and there are several people that was using that. So basically, I incorporate all kinds of possible classification algorithm into a MATLAB package. So you don't need to handle what's the input interface, output interface, and different kind of things. Oops. Okay, thank you. And I want to acknowledge a lot of people here. Without them, it's impossible for me to finish my PhD projects. And thank you all for your time also.